Hello, and welcome to AMAT502 Modern Computing for Mathematicians, Lecture 2. So if you remember on our first day, we introduced this definition of what a Python program is. It's one that consists of a sequence of definitions and commands. This is a very primitive but basic understanding of what a computer program is. And today we're going to go over one of the most fundamental building blocks in programming, which consists of using conditionals to test whether or not an input is true, and then loops to execute an operation multiple times with fewer lines of code. So those of you who are following along with our textbook, John Goodhog, Introduction to Computation and Programming Using Python, what I call the MIT book, this follows roughly sections 2.2 through 3.3. But today we're going to go over basic concepts of if-then logic, branching programs, iteration, and loops. So as a reminder, Python, unlike languages like C++ or Java, indentation is very meaningful. If you don't properly indent parts of the code, you will get an indentation error. This is especially true for if statements, which is the first bit of syntax we're going to introduce today. So the way in which if statements work in Python is you have the expression if space followed by some expression that evaluates to either true or false. That's what a Boolean expression means. It's named after a mathematician by the name of George Boole. And under the assumption that this expression evaluates to true, the following block of code, the one that's indented, is then executed. So first, let's go over what a Boolean expression is. So a Boolean expression are statements that evaluate to either true or false. If you remember, when we introduced the four basic scalar data types in Python, there was a bool, there was an int, a float, and none. So Boolean expressions literally take one of two values, true or false. There are various ways to have an expression evaluate to true or false. Some of those use comparison operators. So we're all familiar from basic mathematics, little less than symbol, or you can flip it around to a greater than. This is strictly less than or strictly greater than. And if I say something like 1 is less than 2, then that evaluates to true. Whereas if I were to say, try to assert that 3 is less than 4, that would also evaluate to true, but 3 is not less than 3. Less than or equal, there's also equals equals. This is, again, very important to note. It's different than a single equal sign because with a single equal sign, we use that for variable assignment. X equals 5 is going to be this assignment to the letter X, value 5. Whereas if I want to say X and it has already some stored value in memory, and then I ask, is it equals 5? There it's testing equality. There's no assignment happening. Also, there's not equals to, sometimes using the exclamation point, sometimes called bang. It's not equal to. And then we have other expressions that we'll get to later in this course, like is not, and in. So if you look at this code block here, and again, if you want to evaluate it, you just hit Shift-Enter. You see I've gone ahead and printed a statement along with how Python actually evaluates that statement and then returns it, which it automatically typecasts into a string so that it's printable on the screen. So this 3 less than 5 evaluates as true, and then this print operation where I've got a string separated by a comma, and then whatever this value of this expression is then automatically converted into a string to be printed. In this case, it's either true or false. Notice that there is an understanding in Python that even if you express 10 as an integer, which is a different type, that's still going to be considered identical to 10.0, which is type float. notice that we also have this weird quirk of Python where I can ask, is 10, I messed up here. So if I have 10 not equals 10, that's going to evaluate to false. Just a quick illustration of how the end statement works. So this works with a lot of different data types, but in particular, if you're presented a string, you ask, is a certain substring inside of here? You can, it'll ask and detect whether or not that substring is inside of there. So CA is inside of the string cat. What about CT? So there's no substring consisting of the letters right next to each other, CT. Okay, so that gives a basic understanding of how Boolean expressions work using the comparison operators. Another fundamental building block is that you're going to need to make use of statements like and or. And as a reminder, if I give you two statements which evaluate to either true or false, then P and Q evaluates to true if and only if both P and Q are true. If just one of them is true, it's not good enough. By contrast, P or Q will evaluate to true so long as at least one of the statements involved evaluates to true. And as a quick question and reminder, I don't know how many of you are aware of the term tautology, but a tautology is something which is always true and is therefore considered not interesting. And an example of a tautology that occurs in everyday language is when someone says, I might or might not go out tonight. So here you're literally carving out all possibilities and saying that one of them must occur. Of course, that's going to be true. You've outlined all possibilities. If you're in a computer science or an electrical engineering course, you might make use of more sophisticated combinations of and or, such as exclusive or, which is only true if exactly one of the expressions are or, but if are true. But if both are true, it evaluates to false. And then there's NAND, not and, is surprisingly just not, and then whatever the result of P and Q is. So these are not concepts, XOR and NAND specifically are not things we're going to be using in this course. But for those of you who are interested in studying logic gates, you'll probably encounter these terms. All right, so let's return to the basic syntax we're trying to introduce here, which is the if statement. So the way the if statement works is it evaluates the Boolean expression immediately following if. And then if that expression evaluates to true, it evaluates the indented code block. By contrast, if it doesn't evaluate to true, it skips the indented code block and just stops. There's no further action. So, for example, here I have a code block which asks the user to supply an input. This is fun for doing interactive programming, but for your homework, you're usually going to want to work with variables and not ask for input. But let's go ahead and see what happens. So my int is the result of whatever the input to this box is. Let's say I choose 24. 7. I just have to hit enter. So my int is 27, and in my code block here I have is if my int, when I divide with 27, its remainder, so that's what this percent means, it supplies the remainder of dividing by 27. You could also think of this as the result of modular arithmetic. So what is 27 mod 27? If that result is equal to, and when you're testing equality, use two equal signs, equals equals. That is equal to 0. And then we can execute the indented code block. In this case, it's true. And it did print. You entered a number divisible by 27. Now, by contrast, if I were to enter in 5, it would do nothing. It's because we've skipped the indented code block and proceeded to the end of the program. For another illustration, we have the same concept where I'm just asked for an integer and I test divisibility by 2. You do the same thing, but I want you to observe that if I were to forget to indent and try to execute this code block, Python would produce an indentation error. And it will tell you that it expected an indented code block. So in this sense, Python, especially through a Jupyter Notebook, it's incredibly user-friendly. It alerts you to what's wrong and helps guide you to debugging your code. So I need to insert a tab, same thing as 4 spaces. And again. Okay, so we've just introduced the most basic if statement. Test whether a given provided Boolean expression is true, and then executes the code block if and only if that expression evaluated is true. Much more useful thing to do is to have an if-else statement. So the if-else statement provides an exception clause. So if your expression is true, you can execute the provided code block. But in case it's not, else, there's another code block to evaluate, which will only evaluate in the case that it's false. But given that a Boolean expression always has to be either true or false, this is known as the law of excluded middle, some code will be executed. And so you can at least tell that your program has done something. There are, of course, refinements on this. You can also catch further ways in which you failed your Boolean expression. And this is called using an if-elif statement. So elif simply means we're in the else setting of the previous if statement. So we've assumed that that's false, but we're concatenating also the ability to test another Boolean expression. That's elif. So if our first logical expression evaluates to false, we then proceed to the next elif statement and look at its logical expression. And in the case, and only the case that that's true, do we execute the second indented code block. So the logic means that if the second code block was executed, then we know that logical expression 1 is false, but logical expression 2 is true. So we're in the setting of not logical expression 1 and logical expression 2 is true. But then we can go further. We can now look at the complement of both logical expression 1 and 2. And that means we're in a new else situation, but then we can provide a further expression to test and test in further ways in which the previous 2 statements failed to be true, but seeing if some other thing is true. But at the end of the day, you can always have a catch-all where you have this else statement. And this base should not be there. Should always abut directly against the else, just as it is up here. And then that's our catch-all. That'll be executed if and only if all the previous statements were false. So to visualize this and to understand why we think of these as branching programs, we have some input. We test the first expression. If that one's true, we execute the first code block and we stop. No further lines are executed. But if this first expression was false, then we proceed to the next logical expression, which we qualify with an elif statement. But then we look at expression 2. If that's true, we we execute the second code block, and then we stop. And we continue to propagate down until we reach this last else code block, which will execute assuming none of the previous statements were true. All right, so here's a simple example of a branching program. And remember, the hashtag means this is not compiled or interpreted by the Python interpreter. And it's just meant to be a little comment for us as humans to read and understand what's going on. So here's a function that takes in 2 integers and returns the largest. And again, remember, when we define a function, we give it a function name, which cannot start with a number, has to start at least with a letter, and cannot use any certain special reserved words, such as I can't define my function to be DEF, because DEF is a reserved term for defining a function. Anyways, we supply the function name, just like in math, we normally call this f. And then we also provide the arguments. And these are meant to be sort of abstract variables, which can take in different values. And then when you call this function, you call it in such a way that binds values. This is something we'll explain further in another lecture. So once we define our function, taken our two values, and now we use an if statement. So if x is greater than y, so again, there's a comparison operator being used there. If that evaluates to true, then we print that x is the largest of the two. Now, in the case that this fails, now there are two ways in which the statement can fail. Either y is greater than x, or maybe x equals y. But in this case, we've assumed that x is not strictly greater than y, and then we ask, well, is y greater than x strictly? If that's true, then we can say with confidence that y is the largest of the two. Now this catch-all, the only thing that this can possibly catch is this sort of middle situation where actually x is equal to y, in which case we can print that x is the largest of the two. But equivalently, we could have said y is the largest of the two, because this statement will only execute if x is equal to y, at least if you follow the logic of the previous statements. So here we are in a code cell, and we can actually experiment and try this. And just to really make clear what's happening, I'm going to go ahead and change the statement and say something like x, comma, is equal to, comma, y. So let's just go ahead and call this code cell a few times. So I provided 37 and 42. You see that 42 is the second argument. That means it's bound to the value of y. And indeed, y is larger than x, so this is executed. But if I were to make both arguments 42, then we'll print this last statement, which gives us a way of testing where in the program did our argument evaluation put us. It tested the first case, is x strictly greater than y? Well, 42 is not strictly greater than 42, so it skipped this. It then proceeded to elif and then asked, is 42, which is y, strictly greater than 42? No, it's not. So it skips finally to our else statement, our catch-all. And because we've thought carefully, we know that we could say that 42 is equal to 42. All right, so let's continue. So in this course, we're not going to talk much about computational complexity, but it merits some discussion. In our first lecture, we defined a program as a sequence of definitions and commands. Normally, if there's nothing fancy going on, we're just doing variable assignment and the basic operations on arithmetic. This is an example of a straight line program. It reads from top to bottom, reading each line from left to right, so that a program with n lines of code will take approximately n units of time to execute, assuming it takes roughly the same amount of time to execute each line. By contrast, a branching program is one where you can skip large bodies of the program, so that even if your code looks very lengthy, perhaps you early on encountered a sort of catch statement, an if statement, that told you to skip and immediately halt evaluation of the program. So here you have an example of a program with n units in lines, which take less than n units of time to execute. So let's go ahead and see this in action and look at the following program. And we're going to try to figure out how many lines are executed depending on the input. So again, just to make this more interactive, I'm using the input argument. So let's go ahead and play around with what happens. So it asks me for an integer. Let me go ahead and input in 0. All right, so I see it prints that 0 is less than 50. And if I can read my code body, I can see that my program halted at this line, which means that it evaluated a total of 4 lines of code. First was the input, then there was our first if statement, which asked if x was greater than or equal to 0, and whether it was less than or equal to 100. So remember, both these statements have to evaluate to be true in order to evaluate everything in this first in this indented code block. That passed that test because 0 is obviously greater than or equal to 0 and less than 100. And then went to our next line and asked if it was less than 50. And indeed, that's where it evaluated, and it stopped because that expression was true. It skipped all the remaining lines of code. So even though this program has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 lines, it only executed 4 of them. But again, this depends on the input. So if I hit Shift Enter again, and I put in 542 or 3, notice, let's think, how many lines of code were executed in this case? So of course I had my input, so there's 1. I then went to my first code block and asked if it passed these tests. It failed. It failed to be less than 100. And so then it proceeded to this else statement. And then it printed this line here. So again, there were only 4 lines of code executed here, but a different 4 lines. So let's try another one. Let's do 65. So I can see that it executed this line. And if you go through and you count, you can see that this was executed, this was executed. It tested this one, but failed. That's our 3rd line of code. It then went to this one, tested it. There's the 4th line. It failed. It didn't execute that one. So then it proceeded to this 5th line and then automatically evaluated this line. So there were 6 lines of code, or 7 lines. 1, 2, 3, 4, 5, 6. 6 lines of code. So even though this is a program of 10 lines, depending on the input, different numbers of lines are executed. Okay, so in class, we spend some time going ahead and trying to write a program that accomplishes this goal. So I've already given you the code for how to determine whether or not one of 2 integers is larger. So in this setting, I want to consider problem. Suppose you write a function called largest of 3. It takes in 3 arguments, x, y, and z, and then it prints the largest number amongst them. So let's go ahead and take some time to think about that. And this is something we'll do as an active learning exercise during lecture. All right, so if you're watching this, maybe pause and try to do this on your own. I'm going to go ahead and proceed with one way in which you can answer this exercise. And I'll just bring to the point that if this is too simple, try to modify the program so that it takes in 3 arguments, but only returns the largest odd integer. All right, so again, we've created a code cell. And if you need to remember, you can always go into your Jupyter notebook. Up in the top left is a little plus sign. That's going to create a new code cell. So you can proceed typing here. Since I'm here and I already know how I'm supposed to call my function, I'm going to copy this line. You'll notice that it highlights syntax. DEF is reserved words, that's highlighted green. And then it identifies the name of my function, largest of 3. So what's something I can do here? Well, I could just as a first guess, hope that maybe x is the largest of my 3 integers. Let me go ahead and write that. So if x is greater than y, x is greater than z, then I'm going to evaluate, I'm going to print x is the largest integer. All right, so that's optimistic. So now I need to ask myself what could happen if one of those 2 statements evaluates to false. So what can happen in that setting? Well, either x is not greater than y or x is not greater than z, which if you think about it means x is totally out of contention. There's no way that it can be the largest because it is either not larger than y or not larger than z. Remember in De Morgan's laws that when I consider the complement of a statement, ands turn into or statements. Okay, so X is not in contention. What could be the next thing? Well, perhaps Y is the largest. So I can't use another if statement, but I can use an elif statement because I'm in the else setting that the first block didn't execute. So else if, let's be optimistic. Maybe Y is our largest. Z. That happens to evaluate to be true, then we can just print Y is the largest. So now finally, what else could happen? Well, obviously, if we've gotten this far, X is not in contention because either Y or Z is greater than it. So then we ask, all right, we throw X away. We ask, maybe Y is greater than Z. If that's not true, then we're in the situation where we can just say that Z is the largest. And it's possible that there was some equality here, but equality means we can just use one of the arguments to go ahead and print. So else print Z. All right, so I've written my code. Now I'm going to delete all the way back so that I can now test my function. Largest of, and maybe I have 2, 3, and 4. Hit Shift Enter, and agreed. It seems to be doing the right thing. All right, what about 5? 5 is the largest integer. Great. What about making this 6? 6 is the largest integer. Seems to be working. And I can try putting my largest integer in all possible different slots, and it seems to be doing exactly the right thing. Notice in the homework, I'll actually ask you to do slightly different things because I use assert test statements to test your output. So instead of printing, I'm going to ask that you do something like return X converted into a string plus largest. And similarly, we can copy this kind of code, and instead of using a print statement, we'll use a return statement. Y, and then finally Z. And so we can test that this still does roughly what we want. Notice that it surrounds itself with quotes because it's returning a string. And Python wants us to know that what's being returned is a string. And that's completely normal. But what's nice about this is I can test this and ask, does this equal, in fact, this output? Yes, it does. So how I evaluate your programs in an automated way is I make you supply things, usually with return statements, so that I can then have them automatically tested against certain test cases. Okay, so probably now a good time to take a little break, maybe stretch your legs. And whenever you come back, we can start with looping programs. So maybe hit pause. All right, so let's continue. We're now interested in doing things beyond just if statements. And in particular, now we're in the sort of opposite situation, whereas with branching programs, we could execute fewer lines of code depending on values of various inputs. Now we can execute code multiple times, even though there's only a few lines of code. That's the beauty of looping programs. There are 3 broad ways in which we can do this, and today we'll cover 2. While statements and for loops. So while loops operate using very similar syntax to if statements. I have this reserved word, while, and then I again provide some Boolean expression, something that as long as it evaluates to true, I have to do something. And this code block do something needs to be something that Python understands. Again, always remember you need this colon right after either an if or a while or a def once you put that statement there. Sort of cueing to you to return and look at the next indented code block. Now, one thing which we've already started to observe is that the statement true is a reserved word. And in fact, it's an object with a Boolean data type, which evaluates to true. So one thing we could do is just insert a true statement, which will cause this program to loop forever. So I wouldn't recommend doing this on our server, but if you have a local install, you could always do this. And I'll go ahead and try. So Shift Enter starts printing lots of Oompa Loompas, and I'm going to go ahead and hit my little stop button here so that I don't fill up my browser's memory. But you can see that even with just a few seconds, it generated lots of Oompa Loompas. And then it lets me know that at some point I used keyboard interrupt to stop this program, which would have otherwise looped forever. So how do we avoid this behavior, looping forever? And how can we have a conditional which changes through each pass of the loop? Well, this is where we use something called either an incrementing or decrementing variable. And again, to make this more fun, we can always go ahead and have the user supply the number of times we want to see Oompa Loompa. So how does this code work? Well, again, the input statement asks the user to supply something, but input always assumes that the input is treated as a string. But here we want it to be treated as an integer, a number. So just as we did in our first lecture, we have to use int to typecast or change the type of this argument from string to something that is useful, like an integer. All right, so we have number times that's given to us as an input, which is initially treated as a string, which we then convert into an integer, all pairing parentheses appropriately. And so while num times is not equal to 0, I'm going to print Oompa Loompa. But I'm also going to change the value of num times. And remember, in our sort of read, evaluate, print loop for understanding programs, here I'm using a single equal sign, which says I'm going to set num times, this variable, which is currently sort of treated as a local expression, to be num times minus 1. Now, again, right now we just take the assignment, we assign whatever's on the left, the value on the right. What is the value on the right? Well, it looks at what was previously bound to the variable num times, which was whatever this input was. All right, so I may have misspoken by saying it was a local, but it's actually might be a global variable. So we've gone ahead and evaluated num times after printing Oompa Loompa once, and then we decrease this by 1. And that becomes the new value for num times. So that when this executes the while block again, it's now asking, is num times not equal to 0? Where num times is now 1 less than it was before. So we've decreased the value of num times by passing through this code block once. And every time we pass through, we'll continue to subtract 1. This is our counter. So that once we've actually executed this, the original number of times specified, we'll eventually reach this statement where num times is equal to 0, which will then cause this to evaluate to be false, in which case we stop executing the program. So for those of you who have taken C++ or Java, you might remember there are various tricks for automatically increasing or decreasing variables. Python has those tricks as well, but they're slightly different. So if we automatically want to subtract 1, then we can use the expression num times minus equals 1. And that knows that I should take whatever num times was and subtract 1. That's where that subtract there is. Alternatively, for those of you who think of like, incrementing a variable by 1 with like, say, I++, that's treated instead of here as plus equals, but we can always put what we're incrementing by to be a negative number. And so that accomplishes the same thing as subtracting 1. All right, let's go see this in action. So similar thing, user is asked to specify an input. I'm going to say 5. And indeed, this code produces 5 Oompa Loompas. Use a slightly different test case for my, my while loop. Instead of asking whether it's not equal to 0, I asked whether or not this was greater than 0, strictly. Of course, if I put in what I had initially written, I get the same behavior. I get 5 Oompa Loompas. There are other ways of treating this, which maybe involves setting an exterior variable I, which you want to increment and count up to the number of times that was provided by the user. So as long as, let's say, I is less than or equal to times, I'm going to print Oompa Loompa, and then I'm going to comment out this code, and I'm going to do what I just said, where I take I and I increment by 1. All right, let's test and see if this does what we want it to. So I put in 5. I do get 5 Oompa Loompas. But the way in which this works is I've initialized a variable outside my while loop by setting it equal to 1. And now my conditional asks, does that variable, is it less than or equal to the number of times I'm supposed to do that? And on the first pass, it goes through, prints Oompa Loompa, and then increases, and it keeps going. You can play around with this and some of the tricks we just had, so you might want to do that now. All right, so if you want to move on, we can do that. All right, so quick recollection question. So in our first lecture, we already talked about how certain operations like plus and asterisk, which we think of as times, are overloaded, meaning that they can operate on multiple data types and they do different things depending on the types of the objects involved. So in particular, instead of using a while loop, I could have done the following. And I'll go ahead and create a new code. I'm going to do the same thing where I'm going to take in some user specified input, num times. And now what I'm going to do is just print in times All right, so let's hit Shift Enter to evaluate this. And again, I'll keep up with 5. Oops, sorry. That was too quick. All right, so it prints 5 Oompa Loompas, but in a slightly different way, and the formatting is not quite right. So I encourage you to read on your own how you might actually have it use special characters to escape. If I remember correctly, this might be. So one trick, which you need to maybe read up on your own, is if I want to return and have a new line, I can do that using the special string /n. And this will have the effect of creating a new line and then printing Oompa Loompa on the same time. And notice these guys have the same output. And I didn't have to use a while loop. All right, so I'm going to go ahead and skip that and then return to our next exercise. All right, so again, this is something we're going to do as an active learning question in class. our second finger exercise asks to write a program that takes in 10 positive integers and prints the largest number entered amongst those 10. So think about it as you're going to generate 10 input boxes, which then you as the user need to enter in something. And then amongst those, it prints what the largest one that was entered. So I encourage you to think about this on your own, maybe pause, but I'll go ahead and give you a hint. So the hint is this. You don't want to try to do the same sort of branching and testing of cases like we did when we had to find the largest of 3 integers that's supplied as arguments to a function. The branching diagram becomes incredibly large and complicated if you try to test out all the possible cases. Maybe the 5th entered number is the largest. What sequence of ands and nots would you need in order to pick that out? Get hugely complicated. So this is where we need to implement some more algorithmic thinking. So suppose you write your program in a way that as you go through, you take the first value and you assume that that's the largest. So far it is. There haven't been any other ones. So you're going to store that as a variable. Now, each time you're asked again to input a number, you're just going to test. Is this larger than the one that's currently the record holder? If so, make that the new record holder and then move on. And then by the time you're at the end of inputting 10 integers, and indeed with this argument, you could use 100 inputs, it'll return the largest one because you always just remember who's fastest, who's best, who's the current record holder. So take some time to go ahead and implement this. All right, I'm not going to show you the solution of that exercise, and hopefully that was enough. But let's go ahead and we'll talk about it in class if need be. So some more syntax which we need to cover. So we've already seen that if we have while true, that's going to loop forever. But there is a way of breaking out of that, and that's using what's called a break statement. So you want to have embedded inside your while loop another if statement. And in the one situation where that if statement evaluates to be true, you're going to make your indented code block just the word break. And that is going to allow you to exit the while loop and prevent the program from looping forever. So suppose we're trying to find the least common multiple of 2 numbers. And let's suppose they're stupidly large, like, I don't know, 234 and 15,432. Just to make my program appear intelligible, I'm going to change my print statement so that it says something sensical. So just as before, we're going to use a while loop, but we're also going to initialize a variable that keeps track of whether or not where we are marching through this while loop. So let's go ahead and let it be x. Why not? So x is going to be set to 1. And I have a while statement that is always given the argument true. So if there were no break statement inside of here, it would loop forever. But what's going to happen is I'm going to test, is x divisible by 234 and divisible by 15,432? Only if that is true are we going to break and exit out of the loop. So what we're doing is we're trying to find what's called the least common multiple of 234 and 15,432. And we're doing this in a very exhaustive way. We're literally searching all integers from 1 up until the least common multiple is found. And that's done by just incrementing x by 1 each time we pass through this loop, assuming this if statement wasn't true. So I'm going to hit Shift Enter, and let's see how quickly this executes. Almost no time passed. And we've now discovered that 601,848 is the least common multiple of those two numbers. So what does this mean? This means that this while loop has executed 601,000 times, nearly 1,000,000 times. Let's go ahead and up the ante a little bit. Maybe it does, maybe it doesn't. All right, so there it actually paused a little bit. But what did we get? 9,521,544. It's the least common multiple of these two large integers. That means that in that short period of time, this program executed 9.5 million times. That's incredibly fast. This is what computers are built for. And what allowed us to do this exhaustive search is we used a while statement that it was always true, but then we embedded an if statement that allowed us to break out, just to make sure we really understand that this is least common multiple. Ask yourself, what's the least common multiple of 10 and 15? So remember, that's a number that's divisible by 10. It's the smallest positive number, divisible by 10, and divisible by 15. Certainly if I multiply the 10 and 15 together, that's 150. But are there smaller integers that are divisible by 10 and 15? Take a second to think about it. So you might have convinced yourself that 30 is the least common multiple of 10 and 15. And indeed, that's true. It's the smallest integer greater than 0 that's divisible by 10 and 15, because 30 is obviously divisible by 10, and 2 times 15 is divisible by 15, obviously. Okay. All right, got one more bit of syntax. So for loops are very similar to while loops in that they'll execute a body of code multiple times. But instead of having to provide some sort of Boolean statement, we can go ahead and specify how many times to execute the code body. And so the general syntax is for maybe some variable in a sequence. Again, we should have that colon, a but directly there. We'll then execute this code block. So getting a little ahead of ourselves, we can consider the following code block. So for I, and we don't even need to specify I ahead of time, we can just do it completely in line in this sequence. And what I'm actually using here is what's called a list, 0, 1, 2, 3, 4, 5. For each I in this, we're going to march through this list and then in order print 4 times that I. And so obviously we start with 0, 4, 8, 12, 16, 20. So 4 times 5 is 20. All right. Now, it's not convenient to hard code or hand code a sequence with, say, 9 million entries, just like we did when we were trying to find the least common multiple of those two large numbers. So this is where we want to make use of other special functions in Python. And one of them is the range function. So the range, like any function, has arguments. And in this case, it takes 3 integer arguments. The first argument tells us where to start our sequence. The second argument, weirdly, tells us where to stop our sequence. And the third argument specifies what's our step size. So this function is going to produce a sequence of integers that starts at start and then moves by start plus integer multiples of the step before ending at some start plus I times step, where this value surpasses or equals the stop value. And it'll be important to remember this or equals, because a little quirk of Python and a lot of computer programming languages that might feel a little unusual. So for example, if I want to print a sequence which starts at 0, stops at 5, and increments by 1, it's going to do something which you might not expect. So it starts at 0, adds 1, 2, 3, 4, doesn't print 5. That's because it's going to end before the second this equals the stop value. Of course, also if it is larger than that. So for example, if I were to make this 2, I would have had this behavior. 0, 2, and 4. Well, that's because the next one would have been 6, and 6 is larger than 5. So something we're going to talk about is how there are ways of sort of shortcutting or providing fewer arguments to a function and still have it do something interesting. So as I defined it, I said range requires 3 inputs. It's not quite true. You could actually give it 2, or you could even give it 1 input. And there's a special meaning when you give it fewer arguments. So if I say range A comma B, that's just assuming you're focusing on the most important things, which is where I start and where I stop. And then it's going to assume that your step size is 1. But again, it's going to be a thing where it starts at A and ends 1 before your stop value. The reason for that is if you go even further and you only supply it with 1 argument, and you say, I want to do range B, it assumes you want a sequence of length B so that you iterate your for loop B times. But like most things in computer science, we start counting at 0. So we execute it with the 0th pass, the 0th entry, and then we stop executing at B minus 1. Because this just has the effect of doing it B times, even though it appears to be doing it 1 less. So just to see how all this works, suppose I do range 1 through 5, and let's suppose I do range 5. And I'll make sure that our print statements produce intelligible outputs. All right. So if I do range 1 through 5, it's going to start at 1 because I told it to start at 1, but it's going to end at 4, 1 less than 5. By contrast, if I do something with range 5, it's going to execute it 5 times, but it starts at 0 and ends at 4. That's because when you count 4 is the number of things including 1, but not including 0. So you have to add back 1. All right, so here's another in-class exercise, which we're not going to explain now. But I want you to maybe study this block of code and try to understand what it's doing. Because here we're going to have a nested for loop. So a for loop inside of a for loop. And I want you to try to really understand what's happening and how many things is this being executed when you go through this, this function. So maybe copy this code into a code cell and see what it does for yourself. I've also done it here, and I'll go ahead and execute it so that you see what the output is. So next time we meet, I'm going to make sure that we actually go through and understand and can explain why is it doing this. And we're going to learn to read a program, a code block, just as if it were a story. And try to understand what is the logic of the story. Okay. So I think there's one last thing we want to talk about, which is I've told you about a sequence of integers, and I first gave you an example. I presented it as a list using square brackets 0, 1 through up to 5. I also said you don't need to hard code this sequence. You can use the range function, and that'll automatically do something. But these are all instances of structures which are called iterables. There are things you can iterate over. And a string is actually naturally an iterable, something that you can go ahead and step through one character at a time. So here's a little funny behavior of the for loop. So for I in cat, we can print I, and it does exactly what's shown. It starts at the first entry, prints that first entry, and then loops, and then goes to the next entry of the string. So I could have also changed this to loompa, loompa. And it'll iterate through, understanding that spaces are a character too. And so this is an interesting way of taking in maybe input and stepping through it. All right. Now, of course, one of the tricks we're going to want to do is, suppose we have user input, or part of that string includes numbers of interest. So suppose I want to total up all the integers in a string. So I can start by initializing total to be 0. And then I can step through the sequence of ones and zeros. Maybe I'll throw in a few more just for novelty's sake. So I'm providing it a string, and it's going to iterate by marching through. Now, what I want to do is update the value of my total by taking whichever element of the string I'm in, and assuming it's an integer, turn that bit of string into an integer by using our int function. So again, this has the process of typecasting. So if something you can turn into an integer, it will turn it into an object of type int. However, if this were like the letter A, it would produce an error because you can't turn A into an integer. So let's go ahead and do this. All right, cool. So I've been able to update the value of my totals. I step through by taking each entry in this long string of numbers and turning that entry into an integer and then adding it to my total. Let's go ahead and see what happens if I put an A there. All right, it'll say invalid literal. So that just shows that int will trigger an error if you try to feed it a letter, something that's not obviously an integer. All right, so this brings us to our last finger exercise, which again, I'm not going to go through here. Something we'll discuss in class, or something for you to work on as your homework. So I want you to write a program that takes in a string of decimal numbers that I assume are separated by commas. Maybe this is my height measured in meters, separated by my weight measured in kilograms. And I want to go ahead and just sum up all the integers involved in that expression. So suppose I take in 1.5, comma 6.4, comma 3.8. So what I want you to do is write a for loop where you're going to step through this string. And if it's something you can turn into an integer, then go ahead and start adding it to a total. But if it's something like a period or a comma, I want you to use some if logic to skip ahead, or maybe just add nothing to your total, so that you can proceed to march through and total up all the integers involved in this expression without triggering an error. So this should take you maybe 10 minutes to figure out. And we'll go over the solution to this in class. Okay, well, thank you very much for your attention. I know this might be a lot at once, but I want you to be able to watch this video, stop, do exercises as you need, and then we'll use our class time as time for discussion. All right, so that'll be all, and I look forward to seeing you in class.